Okay, I think we can get started. So hey everyone, so today what I want to be talking about is like real-time machine learning. And so the idea is typically whenever you're working with some machine learning algorithm is what you do is you have some sort of data set and then you train on it as a data set, like in batches, use many batches, and then you make, train a model. And then similarly, when you're making predictions, you take a whole batch of predictions and make a prediction. But like instead, like let's say, you're running some sort of real-time service, right? And so like let's just start drawing stuff up. So let's say instead like you're running something like a web ranker, right? And so you have like your users, right? And they're coming in and they're requesting like a news feed from your algorithm. And you basically here have like a ranker that takes in requests and returns uh, a list of articles, right? And so the idea is that, like, well, when you're navigating this news feed, you're not just like passively navigating it. Like when a lot of times when people talk about like, well, how do cloud providers get data or anything like that? Well, the way they get it is that you're gonna have a bunch of articles, and then there's gonna be some that you're gonna click on, right? And then this click is basically a signal that should influence how the ranker should behave, right? And so the idea is click, yeah, is a signal that influences your ranker. So if we're to peer under the hood on your ranker, well, like let's look at how it could be trained, right? Like you have this ranker, and this ranker has like let's say the typical supervised learning setting. It has some input data and it has some output data, right? And what this input and output data is, you can think of the input as being an article, and then the output is was it clicked, yes or no, right? So this is a Boolean signal, and then this could be like a vector of like a bunch of data points, like metadata around the article, like the content, some embeddings, a whole bunch of stuff. But the idea is that every time you click, you're basically you're basically creating a new data point for your ranker, and so now like your ranker, basically, do you retrain it on all data or retrain it on new example only, right? So think of it this way, like, well, when you're thinking of a ranker, this is like let's say this is some sort of deep model, right? And so you have a that basically means like you have a bunch of weights W. And so you have these weights W, and then you basically look at a new like you look at an article, right? Like a new article comes in. And is that like at every point where you want to retrain your ranker, you have some existing weights W, and then you basically do a gradient descent on the new weights. There's this article I really liked here, and basically it's this article here by Chip Huyen, and she talks about basically how to do like real-time machine learning. And I think this is a really really good article, so I would highly recommend that you check it out and subscribe to her blog. But basically the idea is like the use case is this: like let's say you're in a setting where latency matters, and you want to make some predictions. So like let's say I think a prime example would be something like TikTok. You have the TikTok recommendation algorithm, and people are coming in and they're clicking on stuff, and you want to very quickly improve the performance of the model. Well, why? Well, let's say that TikTok only aggregated information at their backend like once a day. That means that your ranker is only going to get better for your users once a day. So while they're giving you stuff like I'm not interested in this or I am interested in this, like users are giving you real signals, you're not actually using them. And so they may think like, well, you're not using them and your app sucks. And so I think one of the big reasons why TikTok was so successful in the first place is because their recommendation algorithm is so good. Like I've definitely noticed a huge difference in the quality of recommendations between what my what my sister gets, what I get. Like we both get really what we're looking for. But yeah, so typically I think the setting is sort of like this batch setting is, you have some data. Typically, I think in machine learning we treat everything like a big fat table. But you can imagine that like a more uh, like a more realistic approach is that, well, you have this data, it's in some sort of form of SQL tables. Whenever you want to train it, you like run a query, get some features that you need, and then you feed those queries to an algorithm, right? And so let's say like here, I don't know about this example specifically, but let's take an example, right? Like, let's say you want to figure out like the best destinations in Paris, right? Like, the thing about like a query like that is that you don't expect it to change a lot over time, and you don't actually expect it to change a lot for different people too. Like, you want to go to Paris, okay, you want to go see the Eiffel Tower, see the Champs Elysees, maybe like a couple famous like restaurants or whatever. Like, where did the celebrity go? This information doesn't change all that much across people. But other stuff, like let's say my interest across Twitter, like that's very highly dependent upon who I follow, like my personal interest. And so it almost feels like people are in a different, like on a different website for the most part. And that's because, you really want to treat like recent interactions by users being more important than like, let's say my interests yesterday are much more important than my interest 10 years ago. Um, and so basically here they're saying, well, like to really make online predictions work, there's sort of like two technical problems, right? Like one is the problem of fast inference, as in, well, like I think the example I like to give was back from my work at Microsoft. Like, if you're doing some classification on an email as to whether it's important or not, that classification needs to happen in about the same amount of time that it takes to deliver an email to your inbox. There's a subtlety there because like it's actually not the time it gets delivered; it's more like the time that you read it, right? Like that's the real metric. But for all intents and purposes, let's say it's the amount of time for you to actually like receive this. And so let's see, a pipeline that can process data and return a prediction in real time. Yeah. So like the inference is one piece, and then the training is the second piece, right? As in, can you feed this new model, quickly retrain your model, and then just like deploy it and have it work just fine? So there's a couple of elements here. One is like, just saying like, okay, you want to run gradient descent on this example, that's fine, but then you need to synchronize the weights. Like, are the weights like load balanced, like across multiple servers across the world? How do you do that? How do you deploy them quickly? How do you know if there's issues? What if someone doing a lot of actions? Like, let's say I just like 10 stuff on Twitter. Is the model being trained 10 separate times? Is this being batched in some sort of window? So there's all sorts of like design constraints to think about. But in general, like I would say, like one faster way to make some of these synchronization problems go away is to make the inference faster. And so there's two ways you can make inference faster, right? So one is, for example, have better hardware kernels. Like let's say you write more optimized CUDA code. Another is you do distributed computation. Another is a smaller memory footprint, because generally smaller models are easier to train and faster. And the other idea is like making the models smaller, not using small models. And what that means is that there's sort of three, I think, approaches here. I think here they talk about, like Chip talks about one, which is distillation. Oh no, she does talk about pruning as well. I think she mentions everything. So distillation is basically a technique where you train a smaller model to predict the output of a larger model. That's a way to compress data. Because really what neural networks do is they're basically data compressors. Another one is pruning. So pruning, there's two different techniques. Movement pruning is looking at which parameters are changing the least, and then not changing, like basically just removing them, like zeroing them out and not using them. And another is magnitude pruning. So which parameters have very small magnitudes, also remove them. There's a couple, yeah. So like a survey of compression acceleration. So with hardware, I think there's many approaches you can take here, right? Like this is a wide open field. Like it can go from accelerate some kernels, basically write better optimized CUDA code, use different languages, re-optimize your code, use better compilers, use LLVM. It could also be develop completely different hardware, like think stuff like the IPU or whatever. Um, so I actually talked about this a bunch during my system primer video. But generally, like here, when you're thinking about like you want stuff to be fast, like I basically said, there's four key things that you need. I'll see if I remember all four. So one is replication. The other is caches. The third is queues. Let's see, what was the fourth? Replication, caches, queues. Oh yeah, load balancing. So these are the sort of the four tricks I would say to make systems fast. So replication is, as the name indicates, like replicating a system or data set in various places so that it's easier to access or parallelize. Caches is making sure that whatever you're accessing a lot is easier to access. Queues is a way to send data between two systems in a distributed setting in a quick way. And load balancing is basically a way to balance work over replicated uh, data and models. All right, so these are the like the four tricks, and I have a YouTube video called here the system design primer that goes over these tricks in a lot more detail. And so here, like for example, when people talk about a stream versus batch processing, so there's basically like a couple of tools here that are very famous, right? So historically, if you look at like fast BI systems, like sort of the gold standard is SQL, right? And then this is sort of like maybe the oldest, uh, I don't know, like one of the oldest and most widely used computer science, like just like some of the most widely used software that we've historically used. So it's great. It's very useful. And then, of course, like there's a language, right? But then there's also like an ecosystem around it where you can deploy, and then distribute, and then do whatever you want, right? So more recently, SQL works under like what's called like the ACID constraints, which is basically making sure that your data is there when you commit it, and it works great for stuff like banking software, for example, and when you need to edit stuff. But it doesn't work too well if you're just like, let's say, if you want to do like an append only data set, think like logs, right? Like usage logs. So it turns out other technologies like Hadoop do a better job of solving this problem. And so the way Hadoop works is again like you basically assume like it works under this paradigm called like the map reduce paradigm. And the idea is this, right? So let's say I want to count the total number of users that my app uses, right? And then I have my users distributed over four servers, right? So this is all my users. So what I basically do is I basically map the addition function to sum up all the users for each server, right? So let's say I get 5, 10, 3, 12. And then I do a reduce operation, which is again an addition. That would sum these up, right? And then that gives me the total number of users that I have, even though, but then like the interesting stuff here is like, well, let's say there's duplicates, right? Then having a distinct sum is a bit more challenging to do in this paradigm, but definitely doing a sum. So now if you're doing replication and stuff, you just have to be a bit more careful where you could think you have millions of users, but all you've done is replicate the same user over millions of servers. Um, and so Hadoop works under the batch paradigm, but people have built libraries on top of it, specifically Spark, to do real-time predictions. So, and more recently, a lot of people have been talking about Flink, which is also like there. These are both under Apache, like the Apache like open source community, for also real-time predictions. I'd say here the difference is this is natively, and then this is over Hadoop. Right? So generally, native technologies are better, but uh, ones that built over existing stuff tend to get more users because there's already an ecosystem around it. You don't want to reinvent the wheel too much, and you have an actual business you want to run instead of just like, speculating over like weird tech. Um, and so yeah, so let's go here. Yeah, so that's what they talk about. Okay, so then they talk about the difference between event and request-driven computing. Yeah, I think this is a good figure. Actually, I was going to draw something similar. Um, but basically with request, you're basically like think of the difference is this: like you could either uh, okay, so let's say like it's very important for you to keep track of the total number of users that your app has. There's two ways you can solve this problem. Depending on the importance of this query. One way is to just have a central server that requests everyone and tells them, please tell me, how many users your server has, and then on the central service you aggregate the information. Another way to do it is to basically, instead of uh, requesting it, assume that this is a very important query. And each time any server gets a new user, they would basically send an event to a central log saying, I'm counting that I have this many users. And I know from everyone else that there's roughly this many users. So I believe the total number of users is this. So then all of them end up sending this data to a queue. And what you can then do is like a central server can come into this queue, read in a bunch of values from it, and take the max. And that should be a pretty good estimate of the total number of users your app has. That said, if you have malicious users, like this doesn't work too well because they can just commit like garbage data to you. And so that's why either you want this to be secure or you want it to sort of be decentralized by design. But this sort of gets into like a crypto discussion that I think would be out of the scope for this specific uh, topic here. So I think one of the things I like about like Chip's blog post is that she sort of does a good job of not only discussing the tech but discussing the business impact and like what a company is actually doing and stuff like that. Uh, and so I think she's saying, well, a couple of reasons why this stuff isn't more popular is because like a lot of companies don't see the benefit. And I would actually change this point a bit into that companies haven't gotten very good at doing batch either. Like it's not like batch processing is like this completely solved problem that everyone understands how to do. The other aspect is that, well, managers might not be willing to invest to upgrade their infra a lot for online prediction. So this is sort of a like the sort of like the innovator's dilemma, right? Like what you're doing works fine right now. Like you're gonna keep getting promoted by doing like incremental improvements or whatever else you're currently working on. But taking a speculative bet means like your career is gonna take a risk if it doesn't pay off. Obviously, if it does pay off, you're gonna get very handsomely rewarded. But that's just not often how people actually view risk in the real world. I think like yeah, I mean she does like rightly point out that this it does take a mental shift. uh there's no tables to join. Like you're working with streams, you have to learn like all this new Apache stuff. Like that's different. You have to hire for these people. The managers have to understand the stack and be willing to speculate a bit initially. I think another interesting one is that like it sort of gets back to this common meme where a lot of job postings say they're looking for a machine learning scientist, but what they actually want is a machine learning engineer. And that's just because, like, well, like we've gotten to this point where, if it's not a big fat table that I can access in a notebook, it's just like I don't know what to do. And I think that just like does engineering a big disservice. Like, I think more data scientists should learn the basics of data engineering at least, like just enough to be dangerous. Like, it doesn't have to be your main job if you don't want it to be, but ignoring it completely, I think, does a disservice. And obviously like like it's a higher processing cost just because it means your machines are always on, right? So think of it like when you're batching something, that means that you're only paying for servers while a job is running. But if it's online, it means you're always paying for something. And this can be an issue, like let's say especially if you get demand spikes and having to like elastically adjust like your server requirements. Like this is all just like a general pain in the ass. So here, for example, like, oh, that's interesting. So she's basically saying that there's, where was it? Are there levels here? Level one, online predictions. Yeah. Oh, interesting. Yeah. So level one is online predictions, and level two is online learning. So what online learning, what I believe she's basically talking about is, you can basically adjust the training of your model as you go along, and you can do this adjustment very quickly. And so there's a couple of aspects. Like the main problem with this stuff is that like the problem of catastrophic forgetting. So remember, the catastrophic forgetting was really one of the main motivations for the invention of LSTMs. Um, just because like eventually what ends up happening is that if you feed a network enough data, it's gonna fit really well on recent data and not so well on old data. This may not be a problem actually if you're working with stuff where old data isn't important, but for something where old data is important, this is a huge deal. Um, Yeah, so I also briefly hinted at this. So even after you learn something, it doesn't mean that the new weights are automatically deployed, right? Because especially if you're dealing with like distributed systems and replicating data, one, it's expensive to re-replicate and change your state across, thousands of servers for every new prediction. The second aspect is that even if you did have the infinite resources to do that, just by virtue of time and distributed systems, like different servers are going to be in different states. So this is not even like even feasible within the setting of distributed systems. All right. Oh, interesting. So she does specifically point out TikTok. Like it's very addictive. The recommender system is very good. I think this plays a big part in it. Um, and recommendation systems have like natural labels. So basically, when you click on something, that's a label. That's a strong signal that you liked something. If you stare at something for a long time, that's also a sign that you liked it. And if you just quickly removed it or reported it, then that's a very explicit sign that you don't like it. So think of this like it's very different from like let's say something like ImageNet, where like you have some data that says this is a giraffe, right? And then that means that like some person came in and looked at this and they're like, well, this is a giraffe, and like no one's doing that for fun, like people are we're paying people very little in most cases to sort of sit and do this tedious work, and part of it can be optimized by machines, but for the most part that's not the case. And so whereas with recommender systems there's this inherent advantage where like the more users you have, the easier it is for your recommenders to be good, which is a big reason why like if you look at like something like Bing versus Google, like it's just so challenging to be number two in the recommender space, because number one just gets so much more data, that where they can act, where the model actually becomes better, like it just generally becomes way better and a better experience the more people use it, and then this creates sort of like a virtuous feedback loop that's very difficult to break. Okay, this is interesting. So there's a couple of challenges, I guess, with this stuff. One is that if you're doing learning online, it's very difficult to use traditional model evaluation metrics. Like as in, if you look at stuff like training or test accuracy, like these make sense over a batch of data. But if you're training something on a new example, then what do you do? Like the model trained on data from 10 minutes, is it better than 20 minutes? Like how do you compare them? And I think a big part of it's like that. It's like a big part of it is like A/B testing, right? So what you can do, and people do this quite a bit actually already. Uh, like think of companies like Airbnb and Microsoft, like they all do this. Let's say you have Model A and you have Model B, right? So what you basically do is you deploy this to users like 1 to 1,000, and then deploy this to users 1,001 to 2,000. You're gonna get a bunch of metrics, right? So you're gonna get like average session time. You're gonna get number of clicks, number like amount of ad revenue, uh, and these all of these metrics like represent a scorecard, right? So then what you do is you basically like visually inspect the scorecard, and decide like what do you want to do, like what's more important for you. So that's one way, and then another more automated way of doing is you can basically weigh every element in this scorecard. Like let's say you're like, well, I think ad revenue is the most important, for example. Let's say you're in a very evil company that does this. You're like, okay, for me, like ad revenue is this. Some normalized version of ad revenue, right, where this is like a 0 to 1 value plus like I don't know 0.1 session time, etc. And you basically use this as sort of like an objective key metric that you want to use that you think aligns closely with the goals of your business, and then you basically optimize for this metric depending on what you're deploying. So again, remember this is so different. Like right, like here we're not talking about like training, versus we're not talking about training versus test accuracy or anything like that. Like we're like what we're just talking about in this case is like what metrics are important for the business. Right. Back to this. Um, so parameter servers are like another idea that's used a lot in distributed ML training, where if you have like imagine you're doing data parallelism, so you're training 10 different the same model on 10 different servers across 10 different subsections of your data set. You're going to get a bunch of weights. Then you need to sort of synchronize them in some way. So that's where I first been exposed to the idea of parameter servers. But another setting to discuss it in is in the setting of online learning, where well you're going to be replicating this model across multiple machines, and so you need some sort of like central source of truth, right? And so that's like another idea where like where the servers come in. This is sort of interesting, and so there's definitely I would say like an ML race between like the US and China, as in, I think both countries have serious ML talent that publish a lot. But what Chip is saying is that, well, the infrastructure in China seems more advanced and they're working more in real time ML. And I will say it is one of those things. It's like, well, once you deploy it, you maybe get back to this sort of Google example where just by virtue of you existing first and having this virtuous feedback loop because of recommender systems, it almost becomes like impossible to supplant you. Right. So maybe let's draw it out actually, just see what the feedback loops look like. So let's say you have a model, you know, like basically like so you have an app. So make better, you know, you get more users. In the app itself, more users means more users, right? So this is Metcalfe's law. But you also have like the model makes the app better, the app makes the model better, right? So then there's this double feedback loop here. You know, the model making the app better, app making so app means you're getting more like revenue. Revenue means you can improve the app even more. More revenue means you can hire more people who can get you more revenue and make the app better and make the model better. And so this is just like after thinking about it for 2 minutes, but you can see there's sort of like all these insane feedback loops here. But the main thing I want you to consider is if you have like if you're one of the first to make these feedback loops happen, you can make your models a lot better, a lot more quickly. And it's almost impossible for people to supplant you once you have this advantage. So that's why people are calling it. So LifeEXC1 is asking me like, when do you plan to publish your book, Robot Overlord? So yeah, so I've considered whether I should make it a physical copy or not, but I would say the book is relatively complete at this point. If you just look at the ebook online, like I just figured I want to make it free. Maybe I'll make it available on Gumroad or something with some more chapters. But I just generally say that I think the book is relatively done. I said most of the things I wanted to say. I think the main follow up, which I feel should be a different book at this point, has been more about multi agent learning because it sort of gets into like interesting discussions with like distributed incentives and like game theory. And I felt like when I was writing that it almost felt like a second book. So if I do write another technical book, I think that's probably going to be what the topic is. But I will say thank you so much for reading it. I really appreciate it. Definitely means a lot. Okay, so let's see here. So I have a couple of surveys that I wanted to check out on this topic. So let's see which one looks like the most interesting one. So one is called Continual Lifelong Learning with Neural Networks Review, right? So this is a bunch of people, and there's like in Germany and New York and the Robotics Center in Scotland. Okay, let's see what else is we have. So we also had this end-to-end incremental learning paper. This looks much shorter, so maybe we'll check the survey first. All right, and then the last paper that we could check out is this one, incremental classifier and representational learning. Okay, I'm very inclined to just check out the survey. So let's do that, and then I can maybe check out the other two and some other stream. Anyway, let me know if you have any questions about any of this, because I'm gonna have a quick sip of coffee right now. All right, apologies. Just answering a quick email. So here, let's look at this. Okay, so here what they're saying is that like, okay, well, humans and animals have the ability to continually acquire, fine-tune, transfer knowledge through their lifespan. This is a good point. Not that like biological motivation is a good way, you know, to motivate certain ML research. But it's just that, like, well, it's true. It's more efficient. Like, you don't sit and retrain every night when you sleep or something. Like, you're just continuously learning throughout the day. So this ability is called lifelong learning, and there's a rich set of neurocognitive abilities. They're very important for computational systems and autonomous agents acting in the real world and processing continuous streams of information, right? So there's sort of like, I guess, two use cases where this lifelong learning is very important. I think robotics is a big one, right? Because you don't want to redeploy your robot every night to learn stuff. You want it to learn stuff on the fly. But also, I would say recommender systems is for me the next obvious place where these techniques are a big deal. So, all right. Yeah, so we have this problem of a non-stationary data distribution, which leads to catastrophic forgetting. Like, yeah, let's talk about this for a second. So in ML, typically there's this assumption called the IID assumption. And so what this means is that it assumes that data that you're looking at is independent and identically distributed. And this is just a very fancy way of saying uh, things don't change a lot. That's what identically distributed means. And independent means is that like a point at like let's say an observation at point X doesn't change your observation at point X plus one. So let's think about a few settings where this totally fails, right? Like identically distributed fails if like let's say a robot goes from room one to room two. Room two is not room one, it's completely different environment, there's completely different characteristics. So there's no identical distribution when it comes to robotics unless it's like something like a warehouse robot that's just doing some sort of repetitive task or something. The other one is independent, right? Like, well, let's take an example of a time series. Well, like the price of an object at time x definitely influences its price at time x plus one. Sorry, t plus one, t and t plus one. So both of these assumptions like just fall flat in both of these settings, and basically like, but they don't fall flat like when it comes to like let's say like images, image classifiers or languages, like this, like it's still an issue because language changes over time. Like you have images taken in sequence, but then it's a video. But like yeah, like in video, there's no IID assumption, for example. Like each frame is dependent on the frames that come before it, and maybe there's even long-term dependencies. Sorry, I'm tripping out right now, but like let's say you have a video, right? And let's say the video is moving forward. Like I have the camera and I'm just like moving forward in space. Well, in this case, like you can uniquely determine basically the next frame based on the current frame, right? Because the angle isn't changing. But let's say I turn in a circle. Then if I turn in a circle, then you're only going to figure out that I turned in a circle once there's the two frames that match, right? And so let's say you take one frame, one picture at every degree. So if 360 pictures, it's going to take 360 pictures for you to figure out like, oh, wait a minute, that was a circle. and that you're actually dependent on that point because maybe small things change, right? Like you do a circle and then there's someone walking, and then you do it again, and then now there's no one, right? So there's no IID assumption when it comes to video, is I guess like my quick point and robotics. And so the problem you end up with is this idea of catastrophic forgetting, right? So let's say, back to our 360-degree example, like if you're really learning to optimize well for the 359th frame and everything before it, like you're definitely going to forget what happened at degree zero, even though that's the most important thing for trying to predict what's going to happen at degree 360, right? So, but anyway, it's not like we can just sort of say this is hard, like and forget about it. Like this is hard, but it also means that we need to figure out how to fix it. And so there's a couple of ways to solve this, right? So one is the idea of structural plasticity. So this is biologically motivated. A memory replay is basically occasionally feeding old memories to your model. So this is used a lot in reinforcement learning. Curriculum and transfer learning is basically making the learning hierarchical, right? So let's say, I want to train you how to basically, I don't know, like let's say you have a grid, right? And you have a box. And I want to teach you how to get this box at the end state, like G. So you need to come in here and you need to push this, right? So let's say you know how to do this. Then another task is I want you to learn how to, let's say there's a wall right here. And then I want you to learn how to push a box and then learn how to jump on the box and jump over the edge, right? So this is a much more complex task. But if you understand how to do this task well, you're much more likely to learn how to do the following simpler task. Like, all right. Yeah, intrinsic motivation is also interesting. So yeah, like you'll see all of these show up a lot in reinforcement learning. These are old. Like none of these are new ideas for anyone in reinforcement learning. So intrinsic motivation is basically, it gets back to this idea of curiosity. Uh, you know, like basically think of it as a loss function that optimizes for seeing new states. Right, and let me just give you a simplified explanation of how this could work. Like, let's say you have some game state, right? Like the game state, like a simulation state, and this involves like the position of objects and their rotation, for example. So you're gonna have like some sort of vector xy, right? Like yeah, like a vector xy, or something like this. Actually, no, like it's gonna be more like you have xy, and then you have k of these, right? So let's say you pass these to some sort of hash function, and then this hash function gives you a value, right? And then the further away a new state is from all the ones that you've seen before, well, the more surprised you are. So that's like a very simple way of understanding intrinsic motivation. Oh, hey, Studamaze, always nice to see you. Uh, yeah, and so then another idea is the idea of multisensory integration. And I think here the like it's not necessarily I would say a solution for this stuff, but the motivation is to basically add more data, right? Like add more data in such a way as that you don't end up with this identically distributed problem, right? So let's say you had so much different sensory data that you all integrated into your problem, then you're not going to end up with, like this distribution shift problem. It's actually, I think, a very common criticism of GPT, for example, is that like, well, if you're training on the whole internet, is overfitting really a thing? And I think the answer to that is a bit nuanced because like in the batch setting, I don't think it is. Like I think you can train just fine on the entire internet and then, like whatever you're gonna add is gonna be incremental. But in the online setting, it becomes a bit trickier, right? Because if GPT is all great on the internet, but then if you feed it new stuff and it just generalizes very poorly, then you can't really say that it's all that great. right? So, but generally, like what I want you to think about, like when we're reading the rest of this paper, like the main problem that we're trying to solve. So, if a human relies on IID data, why is it desirable for ML models? That's a very good question. Because if you did not assume the IID assumption, basically that throws away most models that actually work. Like, think about it, right? Like, let's discuss this example a bit more, right? Like, why is IID a big deal? Let's say you're doing something like logistic regression, right? Like logistic regression. And essentially what you're trying to learn is like, let's say some weights like W1, X1, W2, X2, W3, X3. Well, the first aspect is that this means that you can't treat these independently, that ultimately you're going to have W1, X1 plus W2, X2 plus W3, X3. But you're also going to have W4, X1, X2 plus W5, X1, X3 plus W6, uh, X2, X3, right? So this is, like again here, so this is logistic regression without the IID assumption. So this is if the features have codependencies. But now if you also assume that features can be dependent on themselves, then you also end up with the setting where that you can't just say W1 X1, but you have to instead say W1 of basically so X1 T times X1 T minus 1. Right? So you're actually encoding the time. This is like, so think of this like time dependence, and think of this as feature dependence, right? So why don't we do this? Like, this is a great question. Like, why the hell don't we just do this? Well, the reason is the models are much bigger, so they're slower. In some sense, neural networks do this for you automatically, right? Like they sort of create these pairwise dependencies in deeper parts of layers. So that's one reason why they create like more general features. But you can imagine that because if you have time dependency, well, again, in time dependency, well, why stop at t minus 1? Why not go to all the way to x1 t minus k, where k can potentially be equal to t? So basically, look at the entire history. So the reason there is simple. Basically, there's a computation, uh, like it's computation accuracy versus time trade-off that you need to think about. Well, that's a very good question, by the way. So let's see. So here we're saying, well, we want the model to learn new stuff, but we also want it to be stable. So as in like you don't want at some point, like let's say you have an ML model and you've trained it on a bunch of data, and then a new example comes in. You don't want it to change your outlook of your world entirely. But again, this is very difficult because we run into what's called the induction problem. Right? So what's the induction problem? So the induction problem is, I think, it's another formulation of it is like the black swan. And the idea is that all you've seen are white swans, right? And so white swan, like swan color equals white. Like this is just true, and it's been true for a long time. But it takes one example to disprove a theory. No matter how many examples you add to a theory, you can't rule it out for sure. So there's sort of like an asymmetry between proving things and disproving things. And my point is that it's a lot easier to disprove things. Much easier. So this is like the induction problem by Hume, and then I think this is Taleb is called the black swan. So that's a very important thing to think about, I think, when you're dealing with these things. So you want stability, and like this idea here is like the Hebbian plasticity and positive feedback instability with homeostatic plasticity, which stabilizes neural activity. All right. And so the idea here is that, like, well, when you're learning, some stuff is a lot more rigid than others. Like, let's say, me not touching a hot stove, even though I literally did that yesterday. Like this is like hardwired into my brain. Like, no matter how much more data I learn about the world, like I don't want to forget this. And so, let's say you have an agent. Well, how do you sort of encode that some information is very important to not forget? I think part of it is proportional to the amount of pain. So I think negative rewards are a good way maybe to force hard lessons, and then positive feedback is good to learn new ones. So I think there's role both for punishment and uh, rewards like in the real world. Even though we mostly deal with rewards, I guess, in the reinforcement learning community. No, we do deal with punishments. Like you breaking your robot is a big punishment. All right, yeah. So they're talking here. Well, they're saying like the main application is like multi-agent systems and robots. Yeah, they also talk about here Skinner, right? So Skinner was the guy. He's kind of a psycho actually right now. Like, there's no way you could fund a study like this. But basically, he took a set of babies, and some babies he like whenever they did something good, he showered them with praise, and other babies when when they didn't do a good job, he would like yell at them or chastise them or whatever, like surprise the babies that didn't get yelled at all the time. Adjusted better in life, had better jobs, made more money in the future. So yeah, don't be Skinner, but it's I guess useful that someone did that experiment. But please don't try it again. Yeah, so it's interesting that people did continue work on catastrophic learning. But the idea is that like I want you to think about like this is a hard problem. There's no clear solution to it, and I think that the reason is because here like there's sort of a fundamental asymmetry with the problem of induction. That you just can't like ML isn't going to solve this. Like this is just fundamental to empirical knowledge, right? So but it doesn't mean that you can't make ML systems better and more robust, right? It doesn't It's not impossible. Doesn't mean you can't make it a bit better. Like you can reach this, but you can't solve this. So let's see. So here they talk about Hebbian plasticity, right? So the simplest form is the Hebbian, like, so basically you look at synaptic strength and you update it by the product of the presynaptic activity and postsynaptic activity. So basically you update a neuron proportionally or inversely proportional to uh, like how much it was updated before. And then I want you to look at the Kulo Fitz, I believe, model for neurons. This is taking me back. Actually, I read this paper. Oh, the McCullough Fitz, yeah, McCullough Fitz. I would highly recommend you read this paper. Yeah. Yeah. So they were the first to sort of look at, well, like if you put a signal on a neuron, then it's gonna have a charge, and then the charge becomes proportional to how much it's activated in the input. So I think it's a very, very nice paper. If you haven't read it before, it sort of shows you some of the early motivation behind some of this like neuronal work. Probably won't be helpful for your work or anything, but it's just like a really interesting piece of history. So yeah, like you can sort of think of it like a feedback loop, right? Where like the stronger a synaptic strength is, like the more you activate something, the stronger the strength is. And the idea is that it sort of gets back to, this is the idea. What's his name? The fast and slow guy. Fast and slow. What is this called? Fast and slow. Yeah, Daniel Kahneman actually. So this is a very good book actually, even though it looks like a pop sci book. What's interesting about this book is that it's one of the rare psychology experiments that you can actually reproduce. And it talks a lot about how people have an aversion to loss that's greater than an aversion not to win. And I think this asymmetry explains a lot of why modern economics is really wrong. Oh yeah, so Pseudomaze put the link in the paper, so make sure to check it out. But yeah, I believe that's it. Let me just double check. Yes, thank you. Yeah, so let's go back here. So learning without forgetting, lifelong learning, catastrophic forgetting. All right, so training with network expansion, selective network retraining and expansion. Okay, I think this is interesting actually. So, uh, so there's multiple ways to think about how this stuff would work. So one way, for example, is to think of regularization as a way to deal with stuff changing out of distribution, right? Because regularization prevents overfitting. So this is like one way to deal with it. Another way is to do like what's called like selective. Is this the actual paper? Let me check. I'll check here. Sorry, where was it? Okay. Yeah. So another idea besides regularization is the idea of training subsets of a network, right? So this shows up a lot in the NLP community, where let's say you train some sort of large model like BERT, for example. So you have like these layers. See, I don't want to do this neuron analogy anymore. So what you do is basically you train this for some task, then you take this part of the model and then you fit it into a new architecture. So this is fixed, and then this is trainable, and then you solve some new problem. All right, so let's get back. Was this the paper? No, this was not the paper. This has too many theorems for some reason. No, this is not it. But I guess they do talk about neuron calculus here that you can do have AND gates. This is still a very interesting paper though. But yeah, you see, like these guys like thought about this shit a long time ago, right? Like, and then it's like, well, here's how we build like various neurons and build like simple logic gates, and basically, if you can do a NAND operation, you can build computers. I would highly recommend you check out NAND to Tetris. It's an amazing resource that makes the drives this point home. I think there's a free book. Um, there was also, if I'm not mistaken, someone did a web app where you can do this. Yeah, I don't remember where this web app was. I do remember there was one. It was on Hacker News at some point. Basically, you just like drag in your NAND gates and then you build up Tetris by the end of it. You build an OS, an interpreter, file system, like everything you want, just like from NANDs. It's kind of mind blowing when you think about it, because we sort of take this stuff for granted. Um, Yeah, so another idea here is I think they talk a lot about the idea of memory replay. So the idea of memory replay is that some memories you're going basically you're like any online trained model is going to value recent experiences more than older ones. So you occasionally you keep a cache of old interesting ones and occasionally feed them back to the model. So which what you keep in the cache is also could be a design choice. It can be you can decide what it is. It can be random. It can be, let's say, stuff that change your gradients the most. It can be some stuff that was like the most surprising, or whatever. So this is like I would say probably like the whole literature in of itself. But let's see, do they talk here about how they get them? Okay, one thing I'm curious about if it's like uh, online learning, gosh, example, revise, surprise. Yeah, let me Google that later because I think that may be a longer question to answer. All right, so let's keep going. Yeah, so I guess here, like another thing they talk about is the idea of a curriculum learning. So the idea with curriculum learning is that if oh, let's see, interesting. So if a task is really complex, then you're gonna forget all about it. So I guess that's interesting, right? Because let's say a good analogy is that, like, well, like what are things I do a lot every day, right? Like I start a new pip environment. Like, that's something I do quite a bit. So it's very unlikely that I'm going to ever forget like how to set up a pip environment. But let's say I don't know training unit, that's a bit more abstract and more specific. So I'm a lot more likely to forget the details because I do it less often. And so I think like that's sort of like one motivation I think behind curriculum learning, where you can sort of set up tasks such that you slowly increase the complexity. So basically, let's say if this was a curriculum, then here you learn task one, and then task two, and then task three, and then here at this very point you learn the final task you're actually interested in. The complicated part is you actually have to design a curriculum, like design a curriculum. I don't know how you design a curriculum from data. So you have to basically come in and you have to create like, as many, like a one simulation per task that you're interested in. Uh, and this just ends up being, time consuming, right? So it's no surprise that people don't want to do it as much. Uh, okay, interesting, interesting. So I think this was actually a pleasantly, surprisingly easy paper to read. So I think if we go back here, I think a lot of it was summarized in the abstract because I think I was fortunate in that I've seen a lot of these ideas in the reinforcement learning literature. But the idea is that in the main issue you're dealing with anywhere where you're trying to learn in an online way is that you have this problem of catastrophic forgetting. And in some settings, it's not important. In some settings, it is. So like in recommender systems, maybe not so important. In robotics, it's very important. And so you have a couple of solutions to this. One is having plasticity, so as in have some connections that are very important that you never change. Another one is memory replay, so keep a cache of stuff that you think are interesting. Curriculum and transfer learning, which is basically keeping track of, like basically slowly increasing the complexity of a task as you go along. Intrinsic motivation is looking for uh, tasks that you think are surprising, and multisensory integration is basically making sure that you're never in an out of distribution setting by adding more distributions to your data set. And back to the original application, if you found this interesting, make sure to subscribe to me. Also, make sure to check out this blog by Chip. She's an exceptionally good writer, and she gives good perspectives on ML and industry, like the theoretical problems, the business problems. So it's rare to find writers like her. And so she'll basically talk about like the problems with batch prediction, what problems fit the batch paradigm well, what problems don't. In the online setting, the first step is really making real-time predictions, which involves like having faster inference and making models smaller. And then finally, you have this basically the making the real-time prediction problem, which involves replicating data, which involves like quickly learning and relearning. This is all hard, but if you can crack it, you end up with this sort of virtuous feedback loop where no one's ever going to compete with you, and we've seen this happen already with companies like Google specifically, and nowadays more like TikTok. So yeah, I mean, I hope you start thinking more about like online learning. I think for a lot of people in ML, this is out of our comfort zones because we like to think of, okay, this is our training data, this is our test data, but hopefully, online learning is almost by definition an app, right? Because you need to have the server that like gets in requests and so I hope this was useful to you. And again, if you enjoyed this, please subscribe. I'm gonna go, take a break right now, have some more coffee. So yeah, I hope you enjoyed this, and thanks everyone.